Today we're going to have a look at that thermodynamics prep, an introduction, looking at the Born-Haber cycles, lattice energies, ions, charge density, that kind of thing. There's a lot of phrases in there that just need to be picked apart. Most of you have done really well with that, but there's still just a little bit of tightening up before we move on to the entropy bits. And as I said, we'll do a bit of practice at the end of this week and then a lot more later on next year when we come back. So starting off with, you had to look at the Born-Haber cycle for question 1. They've given you the diagram and then you're putting in the letters. Most people got it all right. The bit that people made a mistake on, let's just get my pen there, sorry. The bit that people made a mistake on was here, sodium and chlorine. You did need to look very carefully at which was being atomized and look at the change of state. Half Cl2 going to Cl, that's the atomization of chlorine, and sodium going from Na solid to Na gas. And a couple of people got those the wrong way round, but the rest of it was all fine. Underneath it, we've talked about the enthalpy of formation is equal to everything else added together. So you can just add up the numbers and then you're left with quite a simple sum to solve, and it comes out as minus 360. Just one or two of you getting 360 and ignoring the sign. A little bit frustrating there, but if you look back, I'm sure you'll realise that you were almost there. Then with part 2, you've got the two values that agree, so that's telling us that the bonding is pretty much 100% ionic. There is a slight difference, a couple of kilojoules per mole, so almost completely ionic, or you could say no covalent character. Remember, covalent bonding is where the pairs are actually shared. Character just suggests that there is a little bit of that going on, or the beginnings of that happening. It's really important that we get the phrasing right. It's not the covalent bonding. They're not covalent molecules. They're ionic that have a slight amount of covalent in there, which is different, again, to polar covalent bonding, where you've got a covalent bond that is ever so slightly ionic and slightly charged. You wouldn't talk about the ionic bonding in the covalent molecule. You would talk about the polar bonds. So it's really important to try and use the phrases right. And then again, silver iodide, that's got some covalent character. Again, character, not covalent bonding. It's not a covalent molecule. And then explaining it. A number of people sort of didn't go into this bit, and so you lost a mark due to the polarization of the anion, because the silver is able to polarize it. Then a sort of classic question about the size of the ion and the ionization energy. So further from the nucleus, you've got more inner shells. Just be careful, you don't have more outer shells. There's only ever one outer shell, but you can have more inner shells, causing a greater amount of shielding, and therefore the force of attraction decreases between the outermost electron and the nucleus, so it's less well held. Generally well rehearsed, people have got that one down from GCSE in the beginning of A level, so that was pretty clear. Part 3, just making sure that you've got your definition there. To form 1 mole of solid compounds from the gaseous ions. It's not also an energy required, it's always released. You are forming a bond, and you can see in there reject energy required. It must be released as its bond formation. Underneath again, generally filling in the table, that was really well done. Just a couple of odds with usually these two, same as before. Looking at which one is the atomization of the sodium and which one is the atomization of the oxygen. So it should be that way around. And again, a couple of people just making a little error there, but generally well done. Then we get into the calculation. This was done pretty well. We've got the heat of formation is equal to everything added together, but there are some 2's in there. We've got twice the atomization and twice the ionization energy. So you're being really careful there, because we've got Na2O, so the balancing there, all those processes, the ionization and the atomization, it needs to happen twice for sodium. So there's a number of you got your 1 mark down here, minus 1916. That was the most popular mistake, because we hadn't put those 2's in. But generally, a lot of people doing the right things, but there's just got to be really, really careful with that attention to detail. Again, attention to detail. Most people had a decent idea of what they were saying, but just didn't always do enough for 4 marks. So 4 marks, there's quite a lot of detail needed there. First of all, more exothermic rather than ignore, greater, higher, larger. Remember, we've got a negative number there. So if it's a greater number, it's actually closer to 0, and so it's got to be a more negative when you explain that. So more exothermic, it is a stronger attraction. So that's the first bit to get over. Why is it stronger attraction? Well, you can see there's 2 points. There's the size. The sulfide ion is larger than the oxide ion, but the charges are the same, and therefore talking about charge density. If you just jump into charge density without explaining why the charge density is different, then you don't always get the mark there. And remember, they are ions, so it's not enough to say the atomic radius. You see, that's a reject that they've already picked up on there. And then finally, what effect does that have? Then you mentioned the idea of stronger electrostatic attractions requiring more energy to overcome, but stronger electrostatic attractions is fine. Calcium ion, not a lot to say here, except some of you numpties that forgot the charge. Unbelievable. We even had a 2 minus in one place, and that's really careless. Remember, it's lost 2 electrons on the outer shell. It's a 2 plus, but the vast majority of us should be getting that. And electron configuration, nice, easy. I don't remember anyone particularly dropping marks there. Then underneath it, smaller. Obviously, we've lost that outer shell of electrons, and therefore you've got more protons to electron ratio, or you could say the same number of protons, fewer electrons, so it's stronger attraction bringing them in. Or simply just they've got rid of that level of shielding, so the nuclear charge is able to pull the electrons in closer. Lots of ways around the same bit, but to pick both marks. And then why does it have such a strong high melting point? The idea of strong electrostatic forces repeated many times because it's in a giant lattice and a large amount of energy to overcome. Most people just went for this one, and therefore a large amount of energy needed to overcome. And then the idea of solutions there, the ions being free to move is the important bit. Question 6, it was just to suggest, so you didn't need to go into too much. That's why it says ignore any discussions of reasons. You've got 2 plus, both of them, same group, so you haven't got a lot to do with charge there, but the idea that the different sizes would have something to do with it. Then parts per million, this is a bit of an old question. Parts per million is still used as an expression. It's not actually on the syllabus anymore, but those of you that get it, well done. It is worth having a sort of basic knowledge of this, and so there's been a few questions here and there about this one. You've got 1 kilogram of solution, so we need to know how many parts that is. So you've got to get the same masses. So you've got 4 grams, 0.1 moles is 4 grams effectively, out of the 1,000 grams of solution. So your parts is 4 over 1,000, and then per million, so 4 over 1,000 times a million, so it comes out as 4,000. Well done those of you that got it, and a few of you that asked. Again, really nice answers. The idea that the sulfur and nitrogen, they're burnt, react with water, and that then reacts with the limestone when it's precipitated out from the clouds as rain. Just be careful. That reaction is corrosion with a C. Erosion is a physical process, that's wind and things like that, small bits of sand actually breaking down a rock. So physical process is erosion, the chemical process is corrosion, and you must get that right. And then finally you've got a choice, again it's a suggest. You could either say the values match very closely, so the ionic model is very strong, or you could say there is a slight difference, so there is some covalent character. Either would be fine, but you must go back to the values. It's asked you in that question to discuss that in terms of the values, in terms of the data. What does the information in the table show you? So without actually talking about the data, you're not going to get the mark. Question 7 then, we've got an atom and an ion with a single positive charge are isoelectric. Therefore, so basically it's asking you what does isoelectric mean. The atomic number of the atom must be one less. If you've got an atomic number of the atom, then it would have the same number of electrons as an ion that has lost one, that had one higher atomic number. So D. Then finally, question 5, last one of the written ones. They're talking about explain the term polarization there. Sodium and magnesium. Explain the term as it applies to magnesium iodide and how it arises. So obviously we want the mention of covalent character in there. And then how it arises, the idea that the iodide ion is big and it may be distorted because the magnesium ion has a higher charge density. So that higher charge density than sodium means that it can pull the electrons back, polarize, distort the iodide ion, which gives some covalent character. How do we show that? You must refer to the experimental and theoretical, so the Born-Haber cycle and the calculation are different. The experimental, the Born-Haber, would be more negative or more exothermic, because that's where the extra strength of the bond is from that covalent character. Then we're on to our multiple choice. Which of the enthalpy change is correctly labelled on the diagram? That's D, that we need twice the atomization of chlorine. The value of X, if you go around your lattice energies and everything else, so what you're looking for there is the heat formation, so it's adding them all up together and you get the answer B. Question 7, lithium iodide, that idea that lithium is very small, so it's able to polarize the iodide ion. Then question 9, which represents the process occurring when the enthalpy change of atomization of bromine. Remember, the atomization is to make 1 mole in the gaseous state from the standard states, so that's A. Obviously B looks very close, but bromine doesn't start as a gas. Question 9, which is following of the exothermic reaction shown below. Well, if we've got an exothermic reaction, so that's a minus delta H over T, then that means that the delta S surroundings is positive. Obviously delta H itself, is exothermic, would be negative. The system, we've got this gas being given off, so that's likely to be positive, and as this reaction happens, entropy should be increasing, so delta S total really should be positive. Question 10, I'll just move on to another page. We've got the reaction carried out, so the standard entropy, then you get the answer of A minus 186. Remember, surroundings equals minus delta H over T. It is already minus, so it's a minus minus, which obviously makes a positive value. So it's plus 107.4 divided by the temperature, and so that gives us C. Change, we should have products minus reactants. Remember to take the moles of each of them, so it's 3 times 32 plus 2 times 189, and then you're minusing the 248 added the 206 times 2. And if you do all of that, and then finally the last two bits in here, we've got number 11, which of the following compounds has the most polarized anion. We can see the anions are all the same. So really what it's asking you for is the most charge dense ion. So the right answer is B. So even though magnesium oxide is really almost 100% ionic, the most polarized one, it will still be the magnesium oxide. And then sodium fluoride. Sodium fluoride, is very small charge dense and very unlikely to be polarized. So you can get rid of D, that's covalent. B makes no sense because you've got a positive ion being attracted towards a negative thing. So you're left with A or C, and because fluoride is so small and charge dense, there's no way that there's going to be any polarization there. So your answer is C. That's it. Well done. Most of that was done really, really well. You're in a really good position. We'll do a few questions. We'll finish entropy this week and do a few questions on Thursday. And then hopefully when we come back, we can revisit it and make sense. But well done on this topic. The work that was handed in was really strong. I'll speak to you all tomorrow.